for many of us, we don't need actually an introduction, but I will still say that he is one of the prominent string theorists and he works on various aspects of string theory, holography, ADS-FT, gravitational physics, and many other things. And today his title of his colloquium is Deconstructing Space-Time. And I will hand it over to Sumit to start the stuff. So welcome.
Thank you. Thank you very much for inviting me to give this colloquium. So this is 1 hour, right?
Yes.
Okay, good. Okay, so I have pitched a colloquium at a level which should be accessible to undergraduate students as well. So I see a lot of experts in the audience. So they should, I apologize for this will be probably be too qualitative and too simple for them. So let me begin with something which we always learn in high school. So we are told that there are 4 known fundamental forces. There is, of course, electromagnetism, and it's responsible for almost everything around us. It's responsible for making of crystals, solids, the DNA molecule, or what have you. Second comes weak interactions. These are the forces which are responsible for radioactivity, and in particular, it causes reactions which make the sun shine so that we can exist. And then come strong interactions. Strong interactions are forces which bind quarks inside protons and neutrons and hold them inside nuclei, so atoms can exist. And of course, there is gravity, which is the oldest known force which we have discovered. Of these forces, electromagnetism, weak interactions, and strong interactions are all described in very similar terms. The language for that is quantum field theory, a particular kind of quantum field theory called gauge theory. And the way in a quantum description we think about these forces is that they're a result of exchange of particles. And those particles have names like photons and gluons and double bosons and what have you. And it's an exchange of particles which causes this force. The important thing is that this all happens in a fixed space-time. The notion of space and the notion of time is fixed once and for all, and everything happens in this fixed background. Electromagnetism, of course, has perhaps a more familiar classical description, which we all know about. They're described very well by Michael Faraday's brilliant insight, invented the idea of a field of force. Gravity is not a force in the usual sense. It is a manifestation of a curvature of space-time. So what general relativity says is that a mass, something which carries energy, in a sense bends curvature of space-time, it bends the space-time itself. It's sort of, this is an artist's rendition of what that can happen. And when another body is in this neighborhood, it feels that curvature of space-times and moves in what it perceives as a straight line, which we call geodesics. So this clearly is very different from our description of the other forces. And this is in fact a source of many of the problems which appear when we try to think of gravity in the same language as in thinking in terms of the other forces. So in particular, it makes space-time dynamical, and one consequence is, of course, gravitational waves predicted in 1915 and discovered directly 100 years after they were predicted. Now, in the classical theory of point particles, as we know, the position and momentum of a particle can be specified independently. And once we know the the position and its momentum at one time, the laws of motion determine them at all future times. This is a famous Laplace machine. We therefore talk about the trajectory of a particle. So here is a trajectory of a projectile, which we learn in school. In the quantum theory of particles, of course, we cannot determine the position and momentum of a particle to an arbitrary accuracy. They are subject to an uncertainty principle. We can describe this by saying that the position of a particle has a quantum jitter or quantum fluctuations. This is a phrase which, of course, has a precise mathematical meaning in quantum theory, but we'll use this phrase quite often. One consequence of this is that there are no well-defined trajectories of particles. So if I consider the motion, if I specify the initial and the final position of a particle in quantum mechanics, then there is no notion that in an in-between time, it actually goes through a particular trajectory. In fact, it can take any trajectory which joins these 2 points. And the quantum mechanics actually tells a rule of how to use these trajectories to compute what is the probability, or more precisely, the probability amplitude for that particle to have that location. The same physics, in fact, holds for fields of force. In quantum mechanics, we cannot measure both the electric and the magnetic field at a given point in space and a given time to an arbitrary accuracy. They are subject to an uncertainty relation, pretty much like the uncertainty relation between X and P. So what this means is that the electromagnetic field is a quantum jitter, or quantum fluctuations. Even though these are words, we of course have an extremely precise understanding of what this means, not only for electromagnetism, but for weak and strong interactions. And this picture I'm showing is actually a computer simulation of the vacuum of quantum chromodynamics, which is the theory of strong interactions. If we extrapolate these ideas to gravity, this would mean that space-time itself has a quantum jitter. Unfortunately, we do not understand this picture at the level of precision which characterizes the picture for the other forces of nature. But there has been a lot of progress, and I'll talk about a progress in one particular direction. There is, of course, one situation where the usual tools of quantum field theory could work. And this happens when the quantum effects are small fluctuations around a background space-time. This is what we call perturbative quantum gravity. For example, you can have 2 very weak gravitational waves, which is scattered with each other. And this would be like scattering of other particles which are subject to other forces. And one might try to use the tools of usual quantum field theory to calculate the effect of this. Rather surprisingly, this kind of approach is something which some of the leading figures of quantum mechanics started investigating as early as 1930. I don't know when the word graviton was coined, but in analogy with the other particles, which mediate the other interactions, we call the particles which mediate the gravitational force a graviton. It turns out, however, that the usual rules of quantum field theory are not adequate to describe even this regime. The theoretical framework breaks down at high energies. What this means in usual quantum field theory, this means that when we go to high energy, there will be more structure to these kinds of forces. And string theory is a proposal for such a structure. It's actually a very conservative proposal for this structure. what it posits is a huge number of extra particles which appear at very high energies. But these extra particles are not just arbitrary things, they are the particles which comprise the harmonics of a string. So this theory hypothesizes that the basic objects are not point-like but extended objects, and the simplest one being a string. There are other objects for higher dimensionalities. In this theory, the graviton is at par with the other force carriers, and matter as well appear as harmonics of the strings. And the laws of string theory overcomes the problems in perturbative quantum gravity. What about beyond the perturbative regime? Namely, what would we do if we want to introduce quantum concepts in regions of space-time which have strong gravitational fields, or even fields which are weak but non-perturbative? The clue here comes from the physics of black holes. Now, in general relativity, black holes are objects from which nothing, in particular, not even light, can escape. They're usually surrounded by a surface which we call a horizon. And now we know that black holes are actually very common in the universe, and they're in fact thought to be a key ingredient in formation of galaxies. However, in a dramatic set of development in the 1970s, started off by a prophetic paper by Bekenstein and followed by the famous work of Hawking, this showed that due to quantum effects, black holes in fact radiate. And they may be considered, and they radiate in a fashion such that they look like a thermodynamic object with a characteristic temperature and a characteristic entropy. The entropy formula is rather intriguing. It's a universal formula. All kinds of black holes to leading order obey this formula, namely the entropy of a black hole is proportional to the area of the horizon divided by 4 times the Newton constant. And it is intriguing in the sense that black holes do not appear to be extensive in the usual sense. In usual thermodynamics, entropy is an extensive quantity. What this means is the entropy is normally proportional to the volume of the object. And if you think of a black hole as an object which is of the size of the horizon, this formula seems to violate this extensivity principle. The temperature which characterizes the radiation which comes out of a black hole is also something very universal. It is related to a quantity which is called the surface gravity, which is nothing but the acceleration due to gravity at the horizon of the black hole. Now, usually, if something is thermal, there is a microscopic origin. For example, we can take a box of gas. We know the box of gas is made out of molecules. But of course, when there are lots and lots of molecules, it is much more convenient to describe the box of gas in terms of different quantities. These are macroscopic quantities like volume and pressure, temperature, and entropy. And one of the things that was realized in the 19th century, that it is quite essential that such objects have a microscopic origin. And from this microscopic description, we obtain a thermodynamic description by a process which we usually call coarse graining. What this means that we forget about details of these microscopic origins and replace them by averages. For example, we forget about what the energies of the individual molecules are and replace it by a concept called temperature, which is roughly the average energy of the molecule. It is important to realize, and probably emphasized by Boltzmann first, that without a microscopic origin, thermodynamics would surely imply a fundamental loss of information. It would mean, since there are large number of data sets which could give rise to the same average, if the average was the only description, it would mean that we will never have access to the detailed information which is contained in the system. Now, in the mid-90s, at this, so what was the, and one of the problems of black holes was to try to understand what is the microscopic origin of black hole. In the mid-1990s, a certain class of black holes which appear in string theory was cracked, and in a series of dramatic developments, the microscopic origin of this class of black holes was uncovered. And one of the surprising things about this development is that this microscopic theory turned out to be a non-gravitational theory. It's a kind of theory which is of the type which actually describes the electroweak and the strong interactions. Now, we don't understand the microscopic origin, in fact, of the most common black holes which occur in nature very well. At least there are proposals for this, which are, usually rotating neutral black holes. Now, these black holes, for which we do understand the microscopics very well, are called near extremal black holes. They have a tiny Hawking temperature. However, since the microscopic theory was known and controlled, and a controlled calculation could be done, one could go ahead and check whether this entropy obeys the famous Boltzmann formula, namely, entropy is the log of the number of accessible states of the system. Furthermore, it turned out that the absorption and the Hawking emission of quanta from such black holes can in fact be quantitatively obtained from standard calculations of the quantum field theory, which describes the microscopics. These calculations indicated two equivalent ways of thinking of Hawking radiation. In one way, there are some quanta microscopic ingredients which are moving on some space which describes the black hole and emitting other quanta which go out in space. So that's this picture. And the other picture is the gravitational picture, where those things are described by waves, gravitational waves and other kinds of waves which can exist, which follow classical equations of motion when the black hole is large enough, and which can be absorbed by the black hole. These two calculations had a precise agreement, but it does not solve the information loss problem, since the two pictures were actually valid in two different regimes. It turned out, providentially, that for the type of black holes which we were dealing with, the calculations in one regime could be extrapolated to a calculation in the other regime, which is why there was an agreement. In fact, a resolution of the information loss paradox is one of the main themes of current research in the field. The emphasis at the present time is to understand this purely from the point of view of gravity itself, but I will not talk more about this. I should emphasize that the remarkable thing about these calculations is that a calculation in a non-gravitational theory reproduces a calculation in a gravitational theory, but the gravitational theory lives in higher number of dimensions. One thinks of a black hole as an object, and there is a transverse direction to the black hole. The physics of Hawking radiation or absorption by the black hole happens in these transverse directions, whereas the microscopic description of the black hole does not involve these transverse directions. Several years ago, Maldacena brilliantly realized that what this, in fact, does is to provide of an idea which has been going around for a while, which is called the holographic principle. The holographic principle, in fact, grew out of another remarkable conjecture by Bekenstein. Now, we saw that the entropy of black holes is proportional to the area of the horizon. Bekenstein combined the area law of the entropy of black holes and the second law of thermodynamics and argued that if you take a big surface and calculate the total entropy of anything which is contained in that region of space, it is actually bounded by the area of the surface and not by the volume. Now, it turns out there are situations where the way I have posed this bound, namely a spatial region which is bounded by a surface, is not quite correct. There are some situations where this is correct. There are other situations where they are not correct. But there are more refined versions which involve null surfaces rather than spatial surfaces, where one indeed has a bound of this type. This bound is also quite intriguing, because if we look at this bound, the left-hand side is an entropy which is in the interior. So this entropy relates to something in the interior of the space. The right-hand side purely relates to the boundary. Normally, one would think that one could have an entropy which is proportional to the volume of that region. What this bound implies is that that cannot be true if there is gravity involved. In Bekenstein's argument, it was crucial that the theory inside contained gravity. So if you put enough energy, a black hole can form. So this led in 1993, 't Hooft and later Susskind to interpret this formula in an interesting way. So they looked at this formula and said that if I look at the right-hand side, at least the numerator, this is the area of the boundary. And if I imagine a world, or imagine that there are degrees of freedom which are living only on the boundary, and those degrees of freedom have no gravitational forces, then the usual textbooks of thermodynamics and statistical mechanics must hold. The entropy associated with those degrees of freedom should be proportional to the volume of the space on which these live. But the volume of the space on which this live is the area of the boundary. So maybe what happens, so they made this very bold conjecture that the physics of gravity is entirely encoded in a theory without any dynamical gravity, but in a lower number of dimensions. This became known, in fact, I think Susskind's paper was called this way, that the world is a hologram. So the entire world is encoded in a lower dimensional theory. This, of course, is extremely weird. However, it turns out that the first indications that such a thing can happen came much earlier than its black hole origins. And the story begins in the 1970s in attempts to understand a completely different area of physics, namely the physics of hadrons. hadrons, which are like neutrons and protons and other things, mesons, what have you, they're made out of quarks, and the quarks have the property they are permanently confined inside these objects. And it turned out, before one discovered the correct theory of strong interactions, which goes by the name of quantum chromodynamics, that the behavior of hadrons can be thought of by considering these hadrons as tiny little strings. This was, in fact, the origin of string theory. After the development of quantum chromodynamics, it became clear these strings are nothing but electric flux tubes. In quantum chromodynamics, if I take a quark and an antiquark, what happens is a peculiar nature of the QCD vacuum that the flux doesn't spread out, but they become collimated, joining the quark and the antiquark and forming a string. And this picture is again a lattice gauge theory simulation where you can clearly see the formation of such a flux tube. However, this posed a big puzzle. Now, normally in a quantum theory, everything has a quantum fuzz. For example, if you consider an electron, which we usually consider as a point particle, as far as we know, it's surrounded by a virtual cloud of positrons. This is inevitable if you combine quantum mechanics with special relativity. We call this the polarization of the vacuum. It's a tiny effect. The effect is always there. And in fact, one of the greatest triumphs of theoretical physics is a calculation of physical quantities which are tied to this effect and which are known to probably the best accuracy known of all physical quantities known in nature. There's something called the anomalous magnetic moment of the electron. Nevertheless, we know that it is to a very good approximation, we can regard this as a point particle. And why? We can do this because electromagnetic theory, the interactions of an electromagnetic theory are governed by a dimensionless number, which is called the fine structure constant. And it so happens that the fine structure constant is very small. It is because the fine structure constant is very small that this formation of the quantum fuzz or the virtual cloud in an electron around an electron is actually a tiny effect, a detectable effect, but a tiny effect. So one can imagine taking a limit where the coupling is actually zero. In this limit, of course, there is no cloud and the electron is indeed point-like. So the summary of this is that when we talk about a point particle in quantum mechanics, this statement itself makes sense if there is a small dimensionless coupling in the problem, and in the limit when this dimensionless coupling is small, the particle is indeed a mathematical point. So we can ask the question that if quantum chromodynamics is a theory of strings, there must be a limit when these strings are infinitely thin. If you see the picture, in real SU3 quantum chromodynamics, I mean, this flux tube looks more like a sausage than a string. It's a fat string. So if you want to regard this as a string, we better find a number which we can imagine which taken to be small. The puzzle was that to lowest approximation, QCD with massless quark does not have a dimensionless parameter. There is no coupling in QCD, which we can tune to achieve this limit. So it was rather unclear in what sense we can regard these things as strings. Gerard 't Hooft came up with a rather surprising answer to this puzzle. And his answer was the following. Now, we know, as I said, the strong forces between quarks are somewhat similar to electric forces. However, unlike electric forces, there are three kinds of charges. We call them colors. What this means, a little mathematically, is that in every point in space and in every instant of time, there is a 3x3 matrix. There are many 3x3 matrices, and the effects of quantum mechanics are that the entries of this matrix fluctuate wildly. What it took proposed is that let us imagine a world where instead of 3, there are some arbitrary number of colors. Let's call it NC. And in a brilliant paper, he showed that if I consider a limit where the number of colors grows very large, the interaction between these flux tubes and strings must become very weak, and the strings themselves become infinitely thin. Now, this might sound like madness because 3 is a number which is very far from infinity. However, 't Hooft, in fact, showed that many phenomenological aspects of meson physics, and later Witten showed even for baryon physics, which are very perplexing from the point of view of the quark model or the usual framework, becomes easily explainable in the large N version of this theory. We still don't know why it works so well. We know that it shouldn't work for everything, but for a large number of things, the large N limit is quite a reliable guide to properties of QCD. So, beginning soon after 't Hooft's famous paper, theoretical physicists tried to make sense of the large N limit of gauge theories like QCD. And of course, theorists are always looking for light under the lamppost. So they started looking at models which are solvable. And an interesting model which is solvable is in fact obtained by taking the theory of QCD, forgetting everything about the fact that we have any space at all. So we have matrices which are just functions of time, and also forget about the fact that there are many matrices. So just take a single n by n matrix, Mij, and consider the quantum mechanics of this matrix. Now, since this is a single matrix, of course, we can diagonalize this matrix. So we have simplified the problem a little bit. From n squared degrees of freedom, we have gone to n degrees of freedom. This is good enough if we are only to look at what are called singlet states of the theory. It's pretty much like when we consider S-wave states of the hydrogen atom. There's an effective theory which involves only the radial coordinate, which is good enough to calculate quantities in the S-wave. These numbers, we can consider them as abstract numbers, at a given time have their own quantum jitter, governed by a Hamiltonian, which I'll write down in the next slide. So, for example, a typical set of values of these numbers is 1.6, 0.6, so on. Another measurement of an ideal system would lead its set of values which are very different. So a little more technically, the dynamics is governed by a Hamiltonian, it turns out, which looks what I wrote here before, here. And what I mentioned about S waves comes from the fact that this Hamiltonian has a symmetry. It has a UN symmetry. And there's an additional condition, the states are singlet under this symmetry, and it is in this case that we can express the theory in terms of eigenvalues. Now, this model was solved as early as 1982 in a paper by Brézai, Tixon, Parisi, and Zubair. And one of the things which became clear in that solution is that these eigenvalues behave like coordinates of NC fermions. These particles seem to be moving on a line in an external potential. When people look back at this model in 1990s, it was realized. So we started out with a set of numbers which are fluctuating and which are also functions of time. They became interpretable as coordinates of some particles which are moving on a line. This line was not there to begin with. This line just came into existence when the number of these colors is very large. What was even more surprising is that this emergent space combines with time in a proper 1+1 dimensional relativistic space-time with approximately local physics. You can always think of taking a set of numbers and think of them as positions of particles on a line. What is non-trivial is that if you take this interpretation seriously, namely really take the line as a space coordinate, generally there is no reason why I should be able to really interpret this as a space of a 1+1 dimensional relativistic space-time. And that is precisely what was realized in the 1990s. Now, instead of thinking, so let me try to explain a little bit how that happens. Instead of thinking of the dynamics of each of the lambda i's, it is useful to think of the density of eigenvalues, which is the number of eigenvalues which lie in a certain range. This is similar to a box of molecules comprising a gas. When the number is small, we can track each of the molecules as they bounce around. When the number becomes large, that of course is a very senseless thing to do. Rather, we can describe the gas in terms of the density of molecules. In the same way, when n becomes large, we should look at the behavior of the density of eigenvalues. And the important point is that when n becomes large, even though the individual eigenvalues have large quantum fluctuations, pretty much like position of molecules in the box of gas, the fluctuations of the density are small. And in the ground state, the density is time dependent. In this problem, this sort of looks like the two pictures which I have just shown. Since quantum fluctuations are small, the theory which describes the dynamics is in fact a classical theory as n goes to infinity. A classical theory means that fluctuations are small, in fact zero. For large but finite n, the fluctuations are present, they are small, and they sort of looks pretty much like this. So the left panel actually shows how the density behaves as some function of time. The right panel shows a kind of a density picture. And as you realize, it sort of looks more like a sound wave, which if we regard the space of eigenvalues as a real space. This becomes a little clearer if you subtract the background value and look at how this happens. This is clearly a kind of a longitudinal sound wave which goes along this direction. So the fluctuations for single n by n matrix can be thought of as waves which move in one space dimension. In fact, these waves are non-linear. The wave packets can bump into each other and can interact. The interactions also turn out to be local in this emergent space direction. And perhaps more surprisingly, these interactions include what would be gravitational forces between these wave packets, again in 1+1 dimensions. So we started with a set of n numbers which obey some rules of usual quantum mechanics, and we found an equivalent description in terms of a one field in 1+1 dimension. The field is the density field. The number of degrees of freedom, of course, remains the same in these two descriptions. In fact, the infinite number of matrix elements get metamorphosed into a space dimension. This, in fact, is the simplest example of holography. The reason why it is relevant to black holes is because the dynamics of a class of black holes in string theory are described by pretty much theories of n by n matrices, but many of them. And it turns out that there is a similar metamorphosis of the internal degrees of freedom. However, we do not understand how mathematically how this metamorphosis works. The lowest energy state of these black holes is in fact an extremal black hole, and they do not emit Hawking radiation. In this case, the region which is close to the horizon is a particular kind of space-time which is called anti-de Sitter space, while the Young-Mills theories which describe these black holes are also quite special. They are examples of what are called conformal field theories, which is why this particular kind of holography is called the ADS-CFT correspondence. The ADS space-times are characterized by the fact that it has a boundary. What this means that if I shine some light from some interior point of the space, it reaches the boundary in a finite time. Every event in the bulk has a holographic image on the boundary. So, for example, a particle which is proceeding from the boundary inwards has a holographic image which keeps expanding. So it's sort of like this. Conversely, an excitation at a point on the boundary spreads in time, gets interpreted as a little lump of energy which goes away from the boundary. This picture, of course, assumes that this emergent space-time, actually time is not emergent, only space, is smooth and nearly classical. It so happens that this happens when the hologram is strongly coupled, namely that the theory which describes the black hole is a strongly coupled theory, and that in fact is a fantastic bonus. Because when a field theory is strongly coupled, it is usually very difficult to calculate anything. But if there is a higher dimensional description, which is classical gravity with some other fields, all one needs to do is to solve some usual differential equations to learn about the field theory. It turns out that this strategy has been used to learn about a wide variety of field theories which have applications to diverse areas of physics, from nuclear physics to condensed matter physics and to the physics of cold atom systems. So let me skip the next few slides. Now I talked about the ground state of these black holes. And a typical excited state is a thermal state, namely that it's like a highly excited state of this field theory which describes the black hole, which can be approximated by a thermal state. It turns out that the bulk description is a geometry which has a black hole in it, rather than pure ADS space. And the temperature of the boundary theory is in fact the Hawking temperature. In a similar way, a non-zero density of the boundary theory corresponds to a charged black hole. I'll now give two applications of this idea of using of gravitational physics to learn about strongly coupled systems. The first concerns hydrodynamics. Now, it's a fact of nature that typical strong coupled systems have a universal long wavelength behavior which are governed by the laws of thermodynamics. It doesn't matter what a liquid is made of, the equation which describes the long wavelength behavior of a liquid is governed by something called a Navier-Stokes equation. It's only the parameters of that equation, like the viscosity and the density and things like that, that depends on the particular liquid, but not the law itself. So one might ask that little ripples of waves described, which is a typical example of a hydrodynamic behavior, how are these ripples described in the gravitational description? It turns out these become ripples on the black hole horizon. Now, I said that if I have a thing as a finite temperature and a finite density, it's some kind of gravitational description which describes a charged black hole. And there is a precise map, in fact, of these ripples of the boundary theory to ripples on the black hole horizon. This has led to new results which were not known earlier in fluid mechanics. One of the results is that any liquid which has such a gravity description has a universal ratio of the shear viscosity to the entropy density. It turns out that the equations of general relativity applied to this situation lead to the equations of hydrodynamics. And there are new terms in higher order hydrodynamics which have been later shown to follow from rather general principles independent of holography. The second application I'll talk about is a process which is called a quantum quench. In a many-body system, a quantum quench is a process where a parameter of a system changes for a short period of time. For example, you can take a magnet in an external magnetic field. At time equal to 0, all the little dipoles which comprise the magnet are aligned along the field. And then very quickly, you just reverse the direction of the magnetic field. And of course, all the dipoles will be in big trouble because they try to go to the lowest energy state, but it takes a time to do that. And in the middle, the system, in an intermediate time, the system is out of equilibrium. So this kind of process excites the system, throwing this out of equilibrium. And one important question about systems like this is about the late time behavior. Does the system settle down to some steady state? If so, does the steady state resemble a thermal state characterized by a temperature? If it does, we say that the system has thermalized. As many of you know, this has been an outstanding problem in physics for the last 150 years or so, to understand how and why things thermalize, a question famously posed by Boltzmann. Till recently, there was very little experimental handle on such a process, but over the past 2 decades, experiments in cold atom systems can be now used to study the details of this approach to equilibrium. There are, of course, in the process, we also discovered classes of systems which do not thermalize. These systems are called many-body localized systems. Another aspect is that when the quantum quench crosses or approaches a critical point, that's a point where the system undergoes a critical phase transition, the response has universal features. That is, many different systems display a similar behavior. Again, recently, such universal behavior has become accessible experimentally. Unfortunately, there are very few theoretical tools to understand this kind of out of equilibrium behavior where the system is really very far from equilibrium at intermediate times. It turns out that the ADS-CFT correspondent is useful to understand this problem for those strongly coupled systems which have gravitational duals. What this means is that you don't expect to understand details of the kind of system of some system undergoing a quantum quench in the lab, but if there are universal features, you might hope to understand those. And that's what has been understood. And the reason why this happens is that what a quantum quench reduces to in the gravitational problem is in fact a time-dependent boundary condition. So what this means is that on the boundary on which this strongly coupled system is living, you're sort of tapping the boundary with some external driving. And of course, what this will do, it will send in waves in the interior. The theory in the interior is a gravitational theory, and gravitation is universally attractive. So these waves will self-attract. And the most common thing that happens is that these waves collapse, forming a black hole. Once a black hole is formed, it emits Hawking radiation and it settles down to a steady state. It can settle down to a steady state because this ADS space is like a box. So any Hawking radiation which is emitted can get reflected and the whole system can equilibrate. This steady state typically would be approximately thermal with a temperature which is given by the Hawking temperature of the black hole is formed. This is a problem which can be studied by techniques of numerical general relativity. And people have done that to a very large extent. It's quite a popular line of research in present days to understand the gravitational collapse in such spacetimes using numerical tools, because typically the equations are too hard to solve analytically. But nevertheless, these are differential equations, so they can be posed, a computer can solve them. It is still much, much easier than trying to solve a strongly coupled quantum mechanical system, which is represented in the boundary. In the boundary theory, this entire process of a boundary being driven, a black hole formed and equilibrate is interpreted as a thermalization of the theory. So this is a little window on a very difficult problem in theoretical physics. It turns out that one has also learned a lot about critical quantum quench and the universal behavior which follows this critical quantum quench. And in fact, these efforts have led to discovery of new universal behavior which was not known before. And the nice thing about this is that while these discoveries happen using these holographic techniques, it turned out that the result which was discovered has really nothing to do with holography, but in fact are generally valid in any relativistic quantum field theory. It's like thinking about a problem in a slightly different way sometimes leads to simple new results which you might have otherwise overlooked. Now, unlike the example of the quantum mechanics of a single matrix, an explicit map which relates emergent space to large n degrees of freedom is not available for most interesting instances of holography. Now, recently there are some developments in the class of models where this can be done, but let me skip over those. Rather, let me ask the question, when is the emergent space-time smooth? While large n theories may generically lead to higher dimensional theories containing gravity, there is no guarantee that the resulting emergent space-time is smooth. And there is no guarantee that the gravitational theory is described only by the Einstein action and not Einstein action plus many higher curvature corrections. Now, it turns out that we do know of some conditions which the large N theory must satisfy for this to happen. And there are examples in string theory where these conditions can be met at strong coupling. But even for such theories, one may ask, what kind of state leads to a smooth gravitational description? Is it true that I take this lower dimensional theory, I take some arbitrary random quantum state of the theory and hope to be able to describe by gravitational physics in a smooth space-time? To answer this question, it turns out that ideas from quantum information theory has in fact turned out to be very useful. And among those ideas, perhaps the most important aspect of quantum mechanics which is involved in this game is quantum entanglement. So let me take a few minutes and describe the main features of quantum entanglement. The story starts with a famous paper here, I think shown in New York Times or Wall Street Journal or something like that, by Einstein, Podolsky, and Rosen, who thought of a thought experiment which they believed showed that quantum mechanics is an incomplete theory. I'll now describe a version of this thought experiment, which is not the original version, but a version which was derived by David Bohm. This is textbook material, but let me go over it anyway. Consider the decay of some spin zero particle like a pion into an electron and a positron. So the pion has spin zero, so the electron-positron system also has a total zero spin. This system is created in a state which is an eigenstate of the total spin. What this means, however, as we know in quantum mechanics, that neither of these particles has a definite spin in some direction. However, if we measure the spin of the electron in some directions, we are guaranteed to find the spin of the positron measured in the same direction is in opposite. So if we measure spin plus half for the electron in the z direction out here, the one for the positron is guaranteed to be spin down. I actually drew it the other way around, electron and positron. The thing is that this will continue to happen even if those particles are flown away from each other and very far, and one of them on Earth, the other in the Andromeda galaxy. In other words, if there are two observers who are who's doing these experiments trying to measure the spin, and they make their measurements on various samples of them, and then meet after many, many years and compare their notes, they will find a perfect correlation between these two measurements. Now, by itself, this is not so strange. I mean, one can concoct instances in classical theory where this happens. But quantum theory gives you something a little bit more interesting. So suppose you, being the one who is measuring, for example, the electron, you measure the spin of the electron either in the x or in the z direction. You have an apparatus which lets you do that. It's your choice. However, your friend who measured the spin of the positron has an apparatus which measures the spin only in the x direction. Now, if you decide to measure the spin in the x direction and find plus half, your friend will of course could measure a spin and find it minus half. However, if you now decide that no, I'm going to measure the spin in the z direction rather than the x direction, what your friend will find is the spin can be either plus half or minus half and with equal probability. This is what the laws of quantum mechanics tell you. The slightly puzzling thing about this is that your friend seems to know instantly what kind of measurement you made. Whether you decided to measure your spin in the x direction or the z direction. Well, Einstein, Podolsky, and Rosen actually posed this paradox in terms of position and momentum and concluded that this violated principles of locality in physics. However, after many, many years, now we recognize that this is in fact not so strange. It does not violate any principle of locality which is required by the laws of physics. Rather, what it exposes is the fact that the state of the electron-positron system is what we call an entangled state. This kind of entanglement can appear between two regions of space, just as it appeared between the electron and the positron, in which case we call it a spatial entanglement. And there are many quantities which measure how entangled the state is. And one of the quantities is what is called an entanglement entropy. This quantifies the amount of entanglement between a region A and a region B of some region of space. In a remarkable paper some time ago, Ru and Takayanagi proposed a strikingly simple way to calculate the entanglement entropy of a subregion of the field theory on the boundary. And what they said is as follows. They said, so this is the boundary, and there is this gray region whose entanglement you are interested in calculating. What they argued that if this theory has a gravity dual which is living in this emergent space, the entropy is actually given by a formula which pretty much looks like the Bekenstein-Hawking formula, but the area which is involved here is an area of a surface of minimal surface area which is anchored on this subregion. This proposal has now essentially been proven in many ways, starting with the work of Lekovic and Maldacena. The reason why it enters in our discussion about smooth space-time is that it is now believed that only states which are highly entangled have smooth emergent space. States which are not entangled lead to structures which cannot be described by general relativity. And there's a lot of circumstantial evidence for that. It is also believed that if you want to reconstruct the emergent space, the space is sort of reconstructed. Like if you want to reconstruct the emergent space inside the Ru-Takayanagi surface, which is called an entanglement wedge, all you need to know is the information of the field theory on this oval circle and not the entire space. There are also ideas which pushes this connection to entanglement further. These ideas propose that emergent space is in fact a manifestation of entanglement. And the entanglement structure can be used to construct this space. Now, I am out of my depth in this subject, but Arpan is somebody who has worked with it. So for the local people, ask him about this. Now, can I take just another maybe 2 or 3 minutes?
Yeah, sure.
In fact, quantum entanglement plays an important role in Hawking radiation. And let me explain a little bit of why it does so. The process of Hawking radiation can be thought of as due to pair creation near the horizon. Now, pair creation is an inevitable fact of quantum mechanics and special relativity, and it happens all the time, all over space. These are the effects which we measure, called vacuum polarization. But when it happens near the horizon of a black hole, this is something very special. Because one member of the pair can escape to infinity and the other member can, which is on the other side of the horizon, falls inside the black hole. These pairs are created from essentially a vacuum state near the horizon, and they are pretty much like the EPR pair which we described. So as the pairs becomes widely separated, the green one goes far to infinity and is detected as Hawking radiation. This actually leads to a very puzzling fact. And the fact is that its entanglement keeps increasing even when the black hole is evaporating. And naively, this is what happens. And this is, in fact, the crux of the information loss problem. Now, there's a lot of current discussion about ways to evade this problem. And this is one of the reasons why one needs a precise meaning for spatial entanglement in a theory of gravity. But in a theory of gravity, this is necessarily a tricky concept because space-time itself is dynamical. What do you mean by a region of space? Because the metric is fluctuating all the time. It of course makes sense in the semi-classical limit, where you can think of gravity as small fluctuations around a fixed space-time. So what we really want is to get a notion of spatial entanglement in a theory of gravity, which agrees with this semi-classical notion, which is the standard notion, but can be extended to the full quantum regime. And recently, we think with Gautam and Sandeep Trivedi and Anurag, we made some progress in understanding this if the theory has a holographic dual. Namely, we could provide an understanding of this concept in the holographic dual rather than thinking directly in terms of gravity. So this is, if this is correct, this is one example of something which is extremely puzzling to understand in a theory of gravity, but can be somewhat understood if space is actually emergent. So let me come to, I had another slide on complexity, let me forget about that, come to an epilogue. The notion of emergent space-time implies that gravity is an effective description of something more fundamental. This more fundamental description can be described in the framework of usual quantum mechanics. In this talk, I have discussed one class of proposals for emergent space based on the holographic correspondence. There are others: space-time foam, loop quantum gravity, causal sets, with various degrees of success. It appears that this view of gravity has enabled us to address some puzzling questions related to black holes. And as a bonus, it has also led to understanding aspects of strongly coupled systems in terms of classical gravity. An important issue on which we have not been able to make much progress is the question of space-like singularities. Now, there are many instances where a time-like singularity has an understanding in a larger theory, because time-like singularity is a singularity at a given point in space which exists for all time. So you can think of that as a thing, some lump there, which appears to be singular if you're not careful enough. But singularities inside neutral black holes or singularities in cosmology, like Big Bang singularity, are space-like singularities. They are not things at a certain point in space. They are singularities in all of space at a certain instant of time. Now, this is a very puzzling thing to understand. And there has been many attempts to understand such singularities using these ideas of emergent space-time, particularly the ADS-CFT correspondence, but the results are rather inconclusive. In my mind, understanding such singularities remains a major challenge, and in fact, it will provide a testing ground for usefulness of these ideas. Thank you for your patience, and sorry for taking the extra time.